There's one particular shape out there that has consumed mathematicians' minds for millennia: the right-angled triangle. For one, right angles are just about everywhere. We see them in everything from coffee tables to buildings, from washing machines to gaming consoles. And two, so many other shapes can be broken down into bunches of triangles, which can be really helpful, as we saw last episode. What's more, right-angled triangles pop up even when we aren't considering solid objects. They're part of the way we use vectors in linear algebra, and understanding them opens up doors beyond the realms of geometry. So it's no surprise that the mathematical methods for calculating stuff about right-angled triangles are really handy to have. I'm Jason Guglielmo, and this is Study Hall Real World College Math. A right-angled triangle is pretty much exactly what it sounds like: a triangle where two of the sides make a right angle. And this humble shape has played a pretty big role throughout history. Thousands of years ago, ancient civilizations realized that when designing certain objects, right-angled triangles are a really handy way to think about them. In fact, archaeologists have actually found stone tablets from about 4,000 years ago, which basically have math problems carved into them about poles leaning against walls, which, if you stare a little, gives you a right triangle. And we know that the Babylonians and other cultures like the Greeks worked out how to calculate the various side lengths of triangles like these. One of the most famous Greek mathematicians, Pythagoras, even has the honor of having a whole theorem about right-angled triangles named after him, the Pythagorean Theorem. You might have heard of it, since it can be considered one of the most important revelations in all mathematics. Although, how much Pythagoras actually had to do with it is up for debate, especially since the Babylonians got there much earlier. Putting the name aside, the Pythagorean theorem gives us a relationship between the lengths of the three sides of any right triangle. First off, notice that in any right-angled triangle, there's always one long side that's opposite the right angle. In math lingo, we call that longest side the triangle's hypotenuse. We also tend to label the angles with capital letters and the sides with lowercase letters, like A, B, and C. Now, this next bit might seem like a bit of a tangent, but stick with me, because it's going to give us the Pythagorean theorem while proving it at the same time. First, take 4 identical copies of any right triangle and arrange them in a square, with the hypotenuse of each triangle facing the middle. Since each side of this new square is made of side A and side B from one of our triangles, that makes the length of each side equal to A plus B. The total area of the big square is the area of the 4 triangles plus this smaller square in the middle. And since the smaller square's sides are all length C, its area is just C squared. Now, there's also another way of arranging our triangles inside the big square. We could put them sandwiched in pairs instead. This time, in addition to the area of our triangles, we have 2 smaller squares. But one has side length A and the other has side length B. So their areas are A squared and B squared. This is where the magic happens. In both cases, the bigger squares have the same side length, A plus B. Since they have the same dimensions, the 2 big squares must have the same area, so we can set their areas equal to each other. And inside both of these big squares, we have the same 4 triangles, even though we've arranged them differently. So the area of each big square is equal to 4 times the area of the triangle, plus whatever other squares we put in to fill the gaps. Since the triangles represent the same amount of area in both cases, they can cancel out on each side of our equation. That leaves us with just our filler squares. That means that the first smaller square we made has the same area as the other 2 squares added together. The first square's area was C squared, while the areas of the second squares were B squared and A squared. So, with some rearranging, we get the relationship we were looking for, which is A squared plus B squared equals C squared. And that is the Pythagorean theorem. If you square the shorter 2 sides of a right triangle and add them together, it's equal to the square of the longest side. It might seem like making observations about triangles and finding relationships like these is a really niche area of math. But this small mathematical fact has all kinds of uses and tells us a lot about how we deal with space. Let's head over to Anne, who's on a backpacking trip. Anne has brought a map of the area she's hiking in, which has a grid on top of it, whose lines are spaced apart by 1 kilometer. She's realized that the spot she's currently set up camp at doesn't have access to water, and she's running low. Fortunately, her map says there's another great spot to camp nearby that's right next to a stream, so she considers heading that way. But she wants to know how far it is to the new site before setting off. And while the lines on her grid only give her the distances in the north-south and east-west directions, she wants the distance directly to the stream. Looking at her map, Anne sees the hints of a right triangle emerge. The grid lines form the shorter sides of a right triangle, with the distance she wants to work out as the hypotenuse. And, as we saw, the Pythagorean theorem directly involves the length of the hypotenuse, the very thing Anne wants. Judging by the grid lines on the map, the two shorter sides of the triangle are 8 and 6 kilometers. So she can plug those numbers into the Pythagorean theorem to find the distance she's looking for. That tells her 8 squared plus 6 squared equals c squared. Then all she has to do is take the square root of both sides to cancel out the squared on the hypotenuse. Plugging all of the numbers into the calculator on her phone, she gets 10 kilometers. She figures it's not too far away and decides to head to the new camping spot and fill up her water. So, whether it's on a map or a graph, working out the distance between 2 points on a square grid is a common use of the Pythagorean theorem. More generally, so long as we know any two of the lengths of a right triangle, the Pythagorean theorem always guarantees we can find the length of the third side. That holds true whether it's the hypotenuse, like in Anne's case, or some other situation where we actually know the hypotenuse and want to work out one of the shorter sides. For instance, consider Noah's decorating dilemma. He's wanted to swap out the picture hanging from a chain above his mantelpiece for some time. He already knows the length of the chain, which is 90 centimeters, and the height of the hook above the center of the mantelpiece, which is 1 meter. So he heads to the thrift store and spots a beautiful painting with a frame 30 centimeters in width and 57 centimeters in height. But he thinks there could be a problem. Because of the way the chain attaches, the narrower the frame, the lower it will be. And if it hangs too low, the picture will hit the mantelpiece. So Noah wants to calculate how low the picture will hang. He sees that the chain attaches at the edges of the frame, and that forms two back-to-back right triangles, where half the length of the chain forms the hypotenuse for each. He also sees that half the width of the frame will form the bottom of each triangle. So he already knows his hypotenuse and the length of one of the other sides of each triangle. Now he just needs the length of the remaining side, which is the length between the top of the frame and the hook. That means using the Pythagorean theorem, he can get the length the picture will dangle. Only this time, looking at our formula, we aren't finding the hypotenuse, so we have to make some adjustments. In order to find our missing side length, we need to subtract the square of the side length we know from the hypotenuse squared, and then take the square root of the whole thing. Using the calculator on his phone, he plugs in all the numbers and finds the top of the frame will dangle just over 42 centimeters from the hook. And since the frame is 57 centimeters tall, that leaves just enough room for it to hang without hitting the mantelpiece. Like we saw with Anne and Noah, right triangles often pop up in physical space, but they also come up in situations that have nothing to do with solid objects. For instance, they can also play a role when looking at data on a graph. Like when we're looking at two or more different properties of something, say the heights and weights of people, we might plot them along different axes. Now, plotting data this way is like a portal between numbers and geometry. Think about two nearby data points representing different people. If the distance between them is small on the graph, it tells us the people are also physically similar in real life. And if we think of their distances in terms of coordinates, we begin to see the hints of a right triangle. The same thinking can be extended to other ideas, whether it's working out standard deviations across complex data, or even defining what similarity is, like when YouTube recommends a similar video. Useful relationships between quantities in the real world have mathematical descriptions in the world of geometry. So not only are right-angled triangles often lurking about in physical space, on a theoretical level, they pop up when we're working with abstract relationships between lots of things. From Noah's picture hanging problem, we can see that sometimes it can take a bit of work to figure out where a right triangle might be lurking, and if so, how to apply the Pythagorean theorem. But once we figured that out, so long as we know the lengths of any two sides of a right triangle, we can always work out the third. But even if we only know one side length, never fear. It turns out if we have an angle in the triangle, we can use another set of mathematical tools to make some headway. That discussion takes us into the world of trigonometry, which is what we'll be looking at in the next episode. Thanks for watching Study Hall Real World College Math, which is produced by Arizona State University and the Crash Course team at Complexly. If you liked this video, give us a like and subscribe. You can learn more about ASU and the videos produced by Crash Course in the links in the description. See you next time.